Here we're asked to solve one inequality, 2x minus 3 is greater than 5, and then take that result and intersect it with the inequality 4 minus x is less than or equal to 3. The reason I know it's an intersection is because it has the word and or the upside down cup. That means intersection. And this is actually going to become interesting when we combine these two statements, these two inequalities at the very end, using the intersection concept. Okay, let's work on the inequality on the left first. 2x minus 3 is greater than 5. First, we'll isolate the x term by adding 3 to both sides. And that gives us 2x is greater than 8. And then we divide both sides by the coefficient. Oh, well, we're going to work on the other one at the same time. That's strange. Okay. So we're going to isolate the x term by subtracting 4 from both sides. We get negative x is less than or equal to negative 1. Now, we still haven't flipped any inequalities because we've not multiplied or divided by a negative number. Okay, next step on the left, we're going to divide both sides by the coefficient 2. We'll get x is greater than 8/2. You intersect that together, not union, but intersect that together with the simplification of the right side. Let's see, we want to get rid of that negative sign, so we're going to divide both sides by negative 1. So we get positive x is greater than or equal to positive 1. I want you to note that we have now flipped the inequality sign in that step. Why did we do that? We flipped the direction because we divided by a negative number. Okay, on the left we simplify. We get x is greater than 4 intersected together with x is greater than or equal to 1. Now we need to write our inequality in its most compact form, so we're going to stack number lines. Don't skip this step. This is important. Then, stacking the number lines, we find, let's see, I have to make this a little bigger. The intersection is going to be take the x greater than 4, intersected with x greater than or equal to 1, and it will equal whatever we draw on the bottom number line. Now, the two important numbers here are going to be 4 and 1. So let's mark the 1 and the 4. Line them up in very precisely on top of one another. Now, on the top, we shaded the region that had x values greater than 4, and we put a round bracket on the 4 because there's no equal portion in the inequality. And the second line, the second number line, we're going to shade everything greater than 1, and then put a boxy bracket on the 1 because it was greater than or equal to 1, so it gets a boxy bracket on 1. Now, to find the intersection, we have to examine each of the three regions and ask ourselves, what does it mean to be at an intersection? It's like, in order to be in an intersection, numbers have to live simultaneously in both of the sets. Now, we know a number lives in the set if it's shaded. So let's look at the region on the number lines to the left of 1. In the first inequality, there's nothing happening. There are no numbers included on the left side of 1. The same for the second inequality. So it certainly cannot be included or shaded to the left of 1 in the intersection, the third line. Remember, in order to be in the intersection, in order to get shading in the final line, you have to live simultaneously. In other words, you have to have shading simultaneously in both of those regions above. Okay, now look at the region between 1 and 4. On the first inequality, we have no shading, so we are not including any of the numbers in between 1 and 4 as a solution to the first inequality. The second inequality, it does have shading. Okay, so we are including the numbers in that region. Well, what's the answer? Are those numbers between 1 and 4 going to be shaded or included in the inequality for the intersection? The answer is no, because the only way they can get in the intersection is if they are shaded simultaneously, in other words, included simultaneously in both of the sets above. They're only included in one of the sets above. That's not enough to get them into the intersection. So do not shade the region between 1 and 4 in the final intersection. Okay, at last we're going to look at the region to the right of the number 4. In the first inequality, yes, we do have shading. All those numbers are included in the first inequality. In the second inequality, yes, we have shading for all the numbers greater than 4. Okay, so what does that tell us about the region for values greater than 4 in the intersection? It tells us that we're going to shade that region. We have to shade it because all those values greater than 4 live simultaneously in the two sets above. That's the definition of combining two sets to form the intersection. Last question now. Is the number 4 going to get a round bracket, meaning we exclude it, or a boxy bracket, meaning that we include it? Well, let's look at the top. In the top set, was the number 4 included? Well, let's see. It's a round bracket. There's a round bracket on 4 because we have x greater, not greater than or equal to 4. We have just greater than 4. So that means 4 is excluded in the top set. It is included in the second set because the shading passes right through 4. But that's not good enough to get it into the intersection. For the intersection, it'd have to be included in both of the sets above. So what kind of bracket are we going to put on the number 4 in the intersection on the last line? A round bracket, which means we are not including the number 4, only values greater. So that's our graph notation. Now let's consider the interval notation. That's everything from 4 to infinity, open parenthesis on the left because 4 is not included, open parenthesis on infinity because infinity is never included. And that's interval notation. Then set notation, curly set bracket, all values x, all real values x, such that x is greater, but not greater than or equal, just greater than 4, curly bracket, and that's our set notation.